We're Team 6, and we'll be presenting CADD-E, the camera-directed driving endeavor. CADD-E, or the camera-directed driving endeavor, was designed as a self-driving golf cart prototype, which is able to drive holes 1 through 9 of Lawrence Country Club completely autonomously. We're using minimal user input to navigate the course, which corresponds to the Society of Automotive Engineers Level 4 self-driving, able to operate under almost all conditions. Since we have a user-facing product, we designed a user-centric, accessible interface where our users can interact with the golf cart and tell it where to navigate. We'll run you through the architecture of CADD-E so that you can get a broad overview of how it works.
So we'll start by explaining the offline mapping and localization modules. Offline mapping is how we represent the golf course in our system, and localization is how we determine the golf cart's position relative to that map representation. To represent the golf course, we took data from OpenStreetMap and we constructed a directed graph data structure using waypoints that trace along the cart path. So all of these nodes in our graph contain information about the global position, so this is just the GPS information, latitude and longitude, as well as localized coordinates in meters. Our primary means of localization is through GPS. So the reason that we made this decision is, first of all, GPS is very cost efficient. Our GPS system costs around $300, whereas other popular options for sensors for localization, such as LiDAR, might cost up into the thousands of dollars. Furthermore, given the outdoor environment at the golf course, there's a lot less interference, which will give us a nice, clear signal.
When designing the user interface for CADD-E, there were two major important considerations that we kept in mind during the whole process. The first being how a golf cart is used during a typical session of golf, and the second being how do we keep the UI simple, streamlined, and easy to use, while also showing the user the necessary information for them to have a successful golfing session. On startup, the user is greeted by a welcome screen with the 4 different tee-off locations that they can use for the duration of their golf session. Once the user selects one of the tee-off locations, the screen transitions into the 2 panels you see to the side of me. The left side of the screen is a screen displaying the information the user needs to have a successful golf session, so that includes the speed of the cart, the hole number, stop and go buttons, as well as a next tee box and next green button. On the right is a map of the Lawrence Country Club and the current location of the cart, which is that red dot right there that you see, and then the next target location, which is that blue, right there, that blue dot right there.
The route planner takes CADD-E's location from the localization module, as well as the target destination from the UI, and generates a path from point A to point B. Because we've represented the map as a graph data structure, we can simply do this process by designating the source node as the node on the graph that's closest to the cart's location, and the target node as the node that's closest to the destination. And then we can run a simple route planning algorithm like Dijkstra's algorithm to generate a list of waypoints that will serve as our general trajectory for the next following steps.
Next, we use the collision space identifier in order to identify objects within the path as well as identifying the path itself. For our specific application, we used a YOLO implementation, which consisted of a 23-layer neural network that was pre-trained. For path edges, we used a canny edge detection method in order to identify the edges of the path as seen on my left. Finally, we have ultrasonic sensors on the front of the cart just in case we can't detect any objects before we get too close to them. The ultrasonic sensors will act as a last resort to stopping the cart before we hit anything.
The goal of the path planner is to generate a much more refined path for the cart to immediately follow. To do this, we take into account the cart's state, including its position, ground speed, and acceleration, provided by the GPS and IMU sensors onboard CADD-E, as well as the reference trajectory from the route planner, which can be seen as the middle line of the path, obstacles provided by the collision space identifier, specifically their position within this space, as well as some hyperparameters, such as the car's maximum speed, acceleration and curvature, the width of the road, and some costs associated with some path attributes. We then convert this system from the Cartesian system, the nice and classic XY axes, to a different set of axes, which are seen right here. So the first axis is distance along the path, and the second axis is lateral deviation away from the path. So as you can see, this simplifies the system a lot. Instead of dealing with a curved path, we're dealing with a nice straight path here to follow. We then generate plausible paths for different final states, including longitudinal distance along the path and lateral deviation away from the path, as you can see right here. We then don't use any paths that intersect with obstacles for obvious reasons, and we select an optimal path based on costs associated with path attributes. For example, we want to minimize lateral deviation away from our reference trajectory in order to stay in the center of the path, and we want to maximize longitudinal distance in order to get us the farthest distance possible. The result is a much more detailed path, including information about the car's position, speed, heading, and curvature for the path's duration. We convert this path back into a Cartesian system, the nice XY axes, and we pass it along to the controller.
The controller is the module which takes the planned path in the series of waypoints and transforms it into an actual command we can give the actuators of the car, specifically a pair of throttle and steering angle. Accordingly, the input to the controller is a two-dimensional array of x, y, velocities, and yaws for the car. In order to get the output of a pair of throttle and steering angles, we use a technique called model predictive control. The basic design of model predictive control is illustrated in the figure. A predicted output, assessed by a model, is combined with a reference trajectory, which serves as input to an optimizer, which considers a cost function and constraints in order to generate the future outputs. To implement the optimizer, we use the CVXPy modeling language within Python, which internally uses the operation splitting quadratic program solver to solve this finite optimization problem. I won't go through all the details, but the important thing to note is that this optimization problem has these constraints, which are dictated by the physical limits of the car, as well as some weights on the optimization problem that we define ourselves through a process of trial and error within simulation. I'd also like to note that we use a kinematic bicycle model. The kinematic bicycle model refers to a model of a vehicle, which is, one, kinematic, meaning that the evolution of the car's state depends only on the geometry of the vehicle. It doesn't actually take into account the forces that are being enacted on the tires. And two, bicycle model refers to the fact that we lump together the front and rear tires. This may seem like an overly simplistic model of a car, but in fact, it's one of the most commonly used models in model predictive control papers for building autonomous vehicles. Here's the actual result of the path planner. We can see that we're starting the car at an offset from the reference trajectory, which is in blue. The controller plans a series of states which bring the car along the reference trajectory. As we can see in the next time step, the controller plans a trajectory which converges with the reference trajectory.
Now that we've discussed the controller, we need to send its output to the actuators so that we can actually control the cart. We implemented our prototype on an AWS Deep Racer, which is a 1/18 scaled version of a race car designed and developed by Amazon in order to test reinforcement learning models. In order to actually communicate between the various components of our system and the Deep Racer, we utilize the ROS, or Robot Operating System middleware. And the heart of ROS is consisted of a ROS graph. In a given ROS graph, you have nodes which can publish messages to a predefined topic. Other nodes can then receive the messages that are published to a subscribed topic. Here you can see the ROS graph for our project, which contains the various nodes that are publishing messages to the rectangles, which are the topics. This is what allowed all of our components to interact with each other. Also, since the Deep Racer natively supports ROS, it was fairly easy for us to send the output from the controller to actually control the car. So here is a node for the controller to publish messages to the various servos on the Deep Racer, which will activate the actuators to control the throttle and the steering angles.
CADD-E's physical system is comprised of two main computers, as well as a bunch of sensors. So the first computer is the Raspberry Pi right here. It's responsible for handling all of the sensor data. It reads in the sensor information, processes it, and then sends it over a ROS topic to the other computer, which is this onboard computer on the Deep Racer, which is responsible for running everything else, including the path planner, the controller, and the UI, etc. The sensors here are the GPS, the IMU, two ultrasonic sensors, as well as a camera. These are all mounted on this mount, which we designed and 3D printed, and it fits nice and snug on top of the car. Using this hardware, as well as our software, which we have previously described, we were able to develop a complete physical system. Here's a demo of what this physical system can do in the real world at Lawrence Country Club.
There's a couple things to note in these clips from our tests. So first of all, the vehicle is indeed moving, which is good. And the vehicle's path generally follows that of the cart path. You can see the vehicle correcting its trajectory as it drives. However, the vehicle doesn't drive along the path for very long before eventually swerving off to the side. And this is for a reason that we have diagnosed and will explain later. One more important thing to note is that the collision space identifier had not yet been integrated with the rest of the system during these tests, so that explains why the trajectories aren't affected by the edges of the cart path or other obstacles.
So to summarize these results, first of all, we were able to achieve an average cycle time of around 250 milliseconds. So that whole process that we have just been explaining would be running on these computers 4 times a second. So this is a more detailed view of what happened during the demo. So these blue dots here, that's where CADD-E thought it was. This here, this line, that is the cart path. And then these black lines here, they are the paths generated by the path planner. So the problem here is pretty obvious. CADD-E thinks that it's off of the cart path, which is an issue because it was on the cart path the entire time. And the path planner actually generated proper paths. It was trying to get back onto the cart path, and the controller successfully carried out those commands to get it back onto the cart path. However, because CADD-E was actually on the cart path the whole time, it really just ended up going and swerving off to the side, which caused it to run off the path. So the issue here is pretty simple. The localization is not accurate enough for our needs. So there's a couple changes that we'd like to make to CADD-E in future work. So the first change is obvious. We would like to improve the localization. So there are 2 different methods that we could use to improve the localization. So the first is called real-time kinematics. So this involves using a tower with an exact known GPS location, and then using that tower's location, your GPS location, and the satellites, you can triangulate the position of this GPS sensor in order to get a very accurate GPS reading down to about a couple centimeters of accuracy. The other approach is called a Kalman filter. So using our GPS data and information from the IMU, we can perform sensor fusion in order to get a much more accurate GPS location. Another obvious change that we'd like to see is to implement CADD-E onto an actual golf cart. This would be a fairly straightforward change, as CADD-E is a very platform-independent system. The biggest change would be modifying what actuators actually carry out the controller commands. So instead of using the depracer servos, we would need to implement a couple different physical systems on the golf cart in order to control it the way that we want. So that's it for our presentation. Right here's a link to our GitHub repo. If you'd like to check out our code base, please do. And now we're open for any questions. Thank you for your time.